হ্যালো এভরিওয়ান, এবার হলো পার্ট আরেকটা ভিডিওতে আমরা এখন কি দেখব? তোমরা সবাই রুবিক্স কিউব দেখেছো আশা করি। রুবিক্স কিউব কি? 3x3 ফর্মে একটা কিউব থাকে, 3x3 মানে 3x3 মানে কি 27, তাহলে 27টা পার্টস থাকবে তার মধ্যে। হ্যাঁ, তো সেটাতে আমরা রুবিক্স কিউব বলছি। এখন রুবিক্স কিউব দিয়ে আমরা জানি মানে ম্যাথসে একটা বিশাল পার্ট আছে গ্রুপ থিওরি, যার থেকে আমরা ভেক্টর স্পেস অ্যান্ড অল দিস ভেক্টর অ্যালজেব্রা পুরোটা আমরা জানতে পারছি। তো সেভাবে গ্রুপ থিওরির সাথে আদৌ কি আমাদের এই যে রুবিক্স কিউবের কোনো মিল আছে? এবং পারমিউটেশন কম্বিনেশন অথবা যাকে আমরা বলি বিন্যাস ও সমবায়, সেটার কি কোনো লিঙ্কেজ আছে? চলো সেটা দেখার জন্য আমরা চলে যাই সপ্তর্ষির কাছে, সপ্তর্ষি ভাদুরী। সপ্তর্ষি, ওভার টু ইউ।
Hello dear students, I welcome you to the series of lectures conducted by Juvenile Gurukul on the auspicious occasion of its 3rd year anniversary. Juvenile Gurukul, a step towards quality education at minimum expense. I am Saptarshi Bhaduri and I am going to deliver a lecture on a basic introduction to group theory and its application in Rubik's Cube. So without further ado, let's get started. Today's topic is group theory in Rubik's Cube. Let's start with a basic overview of the lecture. Rubik's Cube was invented by a Hungarian sculptor named Rubik in 1974. It is basically a three-dimensional combination puzzle with 6 different colored faces. Here you can see an image of the Rubik's Cube. It is basically a 3x3x3 Rubik's Cube. In general, we know that there are around 43 quintillion permutations in a 3x3x3 Rubik's Cube. But there are even more permutations which are not directly visible to us. To visualize them, we need to consider the orientation of the centerpieces. This is called the centerpiece. We need to consider the orientation of the centerpiece with respect to the pieces adjacent to them, that is, with respect to the edge and corner pieces. These pieces, this one, and this one, these are and this one, they are called the edge pieces, and these are called the corner pieces. We shall also discuss a very simple yet creative way to visualize those permutations and derive those extra number of permutations, and hence introduce the concept of a supercube. And we will also use some intuitive analogies to understand those arrangements and show few applications of group theory in the domain of Rubik's Cube. Another part of the discussion will contain an explanation of some forbidden arrangements in the Rubik's Cube, that is, some arrangements that can never be achieved by scrambling a Rubik's Cube, but can be achieved by disassembling and again assembling the different parts of the Rubik's Cube, but it will render the cube as unsolvable unless and until it is assembled again after disassembling. The Rubik's Cube makes everyone curious, so our next subtopic is questioning and curiosities. Ever since the dawn of its invention, Rubik's Cube has always been an object of curiosity for mathematicians as well as common people. There has always been a craze among everyone around the globe for solving the Rubik's Cube, but mathematicians, particularly group theorists, combinatorialists, and probability theorists, were more interested in the underlying mathematical implications of the Rubik's Cube. Many questions arose in their mind, like what are the total number of arrangements possible in the cube? Is there any generalization for that in case of a n cross n cross n cube? Can it be associated with a group, which is a mathematical concept which we will discuss later in this lecture? What is the most unsolved arrangement in the cube? In the cube, the order of two moves or set of moves seem to matter, but is there any set of moves x, say, for which if one does x, then does any other set of moves y, say, and gets an arrangement and does y first and then x and gets back this exact same arrangement? What is the minimum number of moves to solve a scrambled cube? And the questions continue. We in this lecture discuss the following things chronologically. At first, we will discuss number of possible or allowed arrangements in a Rubik's Cube and how to calculate them. Secondly, we will discuss the hidden permutations and the concept of a supercube. And at last, we will discuss the application of group theory in the domain of Rubik's cube. Now we arrive at combinatorics in Rubik's cube. There is a common misconception among people that in a Rubik's cube we have to match colors to solve it, but that is not really the case. In a Rubik's cube, we actually have to match individual pieces to solve it, and it can be easily understood when one handles a mirror cube, in which each individual piece has a unique cuboidal shape of different dimensions. Here I have shown a mirror cube. Firstly, we have to know the basic structure of a Rubik's cube. This is what I meant by the basic structure of a Rubik's cube. Here, the center, corner, and edge pieces are marked. The Rubik's cube basically consists of 26 individual pieces or cubelets. 8 of them are corner pieces. So, for example, this one is a corner piece, this one is a corner piece, that on the back is also a corner piece. Here it is also a corner piece. There are 8 of them. 12 of them are edge pieces. This one is an edge piece. This is also an edge piece. This is an edge piece as well. 12 of them are there. And 6 are centerpieces. This is a centerpiece. This is a centerpiece. To have a solved Rubik's cube, each and every piece or cubelet needs to be at the corresponding positions. For example, a corner piece having colors red, yellow, and green has to be at the junction of red, yellow, and green faces with colors matching with corresponding colored in center pieces. Now, what I mean by this color matching with corresponding center pieces. See this picture. This is basically a picture of a solved Rubik's cube. Here you can see that this corner piece, it has orange, green, and white in it. The white is matching with white centerpiece. The orange is also matching with the orange centerpiece, and the green is matching with the green centerpiece as well. And for the case of edge pieces, an edge piece having colors orange and blue has to be at the junction of orange and blue faces again, with colors matched up with corresponding colored centerpieces. Here see a edge piece, which is this one, say it has colors orange and green. See, orange is matching with the orange centerpiece, and the green is also matching with the green centerpiece. Another example, you can see that here is an edge piece with orange and white color. Orange is matching with the orange centerpiece, and white is matching with the white centerpiece. Another thing to note is that there is a general convention of colors in the Rubik's cube, that is, yellow is always opposite to white, red is always opposite to orange, and blue is always opposite to the green color. Now we have to find the total number of arrangements possible in the Rubik's cube. For that, we disassemble the whole cube. The picture on the right side, shown here, shows us the internal skeleton of a Rubik's cube, where the center pieces are attached to the axis of rotation. We must also note that the position of the center pieces is always fixed and they cannot be arranged or assigned another position. But the corner and edge pieces can be arranged freely. Now we are applying the concept of combinatorics. First, we start with arranging the corner pieces. Since there are 8 corner pieces and 8 positions to arrange them, so when we are putting the first corner piece, it has 8 possible choices of position to go in. The second piece has 7 possible choices, as one choice of position is already been taken by the first piece. Similarly, the third one has one less again. It has 6 possible choices, as 2 are already taken by the first and the second ones. And this continues until the last or the 8th corner piece is left with only one possible choice of position. So the total number of arrangements here are 8 factorial. Now arranging the edge pieces. We know that there are 12 edge pieces. The first one has 12 possible choices of position. Second one has one less, it has 11. Then the third one has 10, one less again. And it continues again until we reach the 12th edge piece, which has only one possible choice left. So the total number of arrangements here are 12 factorial. Now, after arranging the pieces in the Rubik's cube skeleton, we have to consider the individual arrangements also. So at first, we are orienting the corner pieces. Each corner has 3 possible choices of orientation. So 8 corner pieces will count for 3 times 3 times 3 times 3 up to 8 times. That is 3 to the power 8 distinct cases. Now we will orient the edge pieces. Each edge piece has 2 choices of orientation. So 12 corner pieces will count for 2 times 2 times 2 up to 12 times. That is 2 to the 12 distinct cases. Now the total number of permutations we have equals 8 factorial times 12 factorial times 3 to the power 8 times 2 to the power 12, which is this huge number. But this is not the actual number of permutations possible in a 3 cross 3 cross 3 Rubik's cube. It is basically the total number of permutations possible if the cube was disassembled and put together, as some of these permutations will never arise if we were to scramble or solve Rubik's cube. Now we are going to calculate the total possible permutations which are possible when we scramble a solved Rubik's cube. We have to consider some cases. First, it is impossible to have only a single corner twist. Here I have shown a picture. A single corner twist is never possible. So while orienting the corner pieces, we considered that each corner piece has 3 choices of orientation, but that is true only up to the 7th piece, as the last piece has only 1 choice of orientation. Otherwise the cube is unsolvable. So it is 3 to the power 7 rather than 3 to the power 8. Similarly, the second case we have to consider is the case of an edge flip. There is no possibility of a single edge piece when we scramble a solved Rubik's cube. Here I have shown a single edge flip. This single edge flip is never possible when we scramble a solved Rubik's cube. It is only possible when we disassemble it and put it together, that is, assemble it again. So we must consider 2 to the power 11 cases instead of 2 to the power 12 cases. The last case we have to consider is that it is impossible to have just 2 pieces swapped. While assembling the cube, if you put the edges first, the edges can go wherever they like, but the last 2 corners will have 1 choice. So it will be 12 factorial by 2 instead of just 12 factorial. Now total possible permutations are 8 factorial times 12 factorial by 2 times 3 to the power 7 times 2 to the power 11, which gives us this huge number, which is approximately 43 quintillion. Now we arrived at our desired result. But there is still something missing. The case of hidden permutations. So far, we have considered the permutations in the positions and orientations of the corner and edge pieces only. But the 6 center pieces are not considered. It is true that the center pieces cannot change positions, so no permutations can arise from them. But they can change orientations, so permutations must arise from the change in their orientations. But it is not visible as it has a rotational symmetry of 90 degrees, so one cannot distinguish between 2 orientational permutations just by looking at a Rubik's cube. That is why we have to be a little bit creative, and we have to come to the concept of a supercube. This is a normal Rubik's cube, and clearly we cannot see the orientation of the centerpiece. See, the orientation of the centerpiece doesn't matter. Now, the creativity we are going to add is that we are going to draw arrows on each cubelet of each face. And the only convention being arrows on each cubelet on each face points in the same direction. See this figure? See, the arrows in the white face are all facing in the same direction. Again, the arrows in the red face are all facing in the same direction. And in the green face, it is the same as well. Now, while solving the cube without caring about the orientation of the arrows on the centerpieces, 4 cases may arise. I have listed the 4 cases. You can see images. I have shown here the white face with arrows on the edge and corner pieces pointing up. Now, with respect to the arrows on the edge and corner pieces, the arrows on the centerpiece can be parallel. This is a parallel case. It can be anti-parallel. This is an anti-parallel case. It can be 90 degrees clockwise. See, this is the 90 degree clockwise, and it can be 90 degree counterclockwise. This is the case for the 90 degree counterclockwise. Now, we observe the following things in this supercube. Considering a particular colored face, We can swap between parallel and anti-parallel cases, or between clockwise 90 degrees and counterclockwise 90 degrees easily with certain algorithms. Algorithms are basically a set of moves. Now, by applying some particular algorithms, we can change the orientation of arrows on centerpieces without disturbing the orientation of arrows on centerpieces of other colored faces. But we cannot swap between, say, an anti-parallel and a 90-degree clockwise without changing the orientation of arrow on its centerpiece of another face. Secondly, we note that parallel and anti-parallel cases always come in pairs, just as 90-degree clockwise and counterclockwise cases. Now, here comes the part of the calculation of extra permutations. We assign the parallel and anti-parallel cases the parallel symbol and the clockwise and counterclockwise 90-degree cases as the perpendicular symbol, and we make the following table. This table shows us that if there are 0 parallel cases, then there are 6 perpendicular cases and vice versa, and if there are 2 parallel cases, then there are 4 perpendicular cases and vice versa. So we see a total of 4 distinct mutually exclusive category of cases where permutations have to be considered. Now I will show an example video demonstrating the above cases.
So as you can see, this is a normal Rubik's cube. See, there are no arrows marked here, and you cannot distinguish the orientations of the centerpieces as it has a rotational symmetry of 90 degrees. Now this is the super cube I made. See that I've already told you the convention of making the super cube. I have marked arrows on each face, and all of them are facing in the same direction for a particular face, and you can now clearly distinguish between the orientations of the centerpieces. Now I am applying a certain algorithm which I will later discuss again in this video. See, that I have swapped between a parallel case and an anti-parallel case without disturbing the orientations of any other faces in the supercube. And again I can apply this algorithm. And I again get back the parallel case. Now you cannot do it for, like, say, from a you can not turn a parallel case or an anti-parallel case to a 90-degree case without disturbing the other orientations, and that is what I have said earlier about the 4 mutually exclusive cases. So I have said that the parallel and anti-parallel cases are equivalent and denoted them parallel symbol, and similarly I have also said that the 90-degree clockwise and the 90-degree counterclockwise cases are also equivalent, and I have assigned them the perpendicular symbol. Now, for the sake of simplicity, I'll call both the parallel and the anti-parallel cases as parallels, and the counterclockwise 90 degree and clockwise 90 degrees cases, I'll call both of them perpendicular cases. So here the case which is demonstrated is all the 6 faces have 6 parallel arrows. You can have 2 parallels and 4 perpendiculars. You can also have 4 parallels and 2 perpendiculars, and you can also have 6 of them, all of them are perpendiculars. The main thing to note here that there is an even parity which is maintained. Now what do I mean by even parity? This means that the parallel cases, or say the perpendicular cases, always come in even numbers. That has to be kept in mind before we do the calculations. And this is one of the basic things one will observe once he or she makes a supercube using these arrows. So let's move on to the calculation of the different permutations in the supercube.
Now, as you have seen the video, now we have to come to the cases we have to consider to find out the hidden permutations in the Rubik's cube. First case, 0 parallel cases and 6 perpendicular cases. To have 6 perpendicular cases on 6 faces, we choose 6 out of 6 colors. That is, 6 choose 6, and each arrow has two possible orientations for each face, and that counts for 2 to the power 6 cases. Therefore, total cases equals 6 choose 6 times 2 to the power 6, as these two are AND cases. Second case is 6 parallel cases and 0 perpendicular cases. It is a similar case, so doing the calculation, we get again 6 choose 6 times 2 to the power 6 total number of cases. Third case is 2 parallel cases and 4 perpendicular cases. To have 4 perpendicular cases on 4 faces, we choose 4 out of 6 colors. That is 6 choose 4, and each arrow has 2 possible orientations for each of these 4 faces, so that counts for 2 to the power 4 cases. Now 2 colors are left, that is 2 parallel cases, so we choose 2 out of 2 colors, that is 2 choose 2, and again orienting the arrows in 2 possible orientations for 2 faces gives us 2 to the power 2 cases. Therefore, total number of cases equals 6 choose 4 times 2 to the power 4 times 2 choose 2 times 2 to the power 2. These are all multiplied as all of them are AND cases. Fourth case we have to consider is 4 parallel orientations and 2 perpendicular orientations. It is similar to the third case, so we do the similar calculations, and this leads us to the total number of cases of 6 choose 4 times 2 to the power 4 times 2 choose 2 times 2 squared. Now we add all those mutually exclusive cases to get total possible cases. These mutually exclusive cases are all cases, so we are adding them to get the total number of permutations. The total cases considering the different orientations of the arrows are 2 times 6 choose 6 times 2 to the power 6 plus 2 times 6 choose 4 times 2 to the power 4 times 2 choose 2 times 2 squared. Now we are taking 2 to the power 7 as common, and we are left with 1 plus 15. Now 1 is this 6 choose 6, it is basically 1, and 6 choose 4 is 15, and 2 choose 2 is 1 again. So we are taking common 2 to the power 7, and we are getting 1 plus 15 inside the brackets, which gives us 2 to the power 7 times 16, which is basically 2 to the power 7 times 2 to the power 4, which is 2 to the power 11. So we multiply the previous number of cases by 2 to the power 11 number of extra cases to get total number of permutations, that is permutations considering orientation of centerpieces, which is equals to 8 factorial times 12 factorial by 2 times 3 to the power 7 times 2 to the power 11 again times 2 to the power 11, which gives us this huge number, which is approximately 8.86 times 10 to the power 22. So these are the total number of permutations possible in a supercube. I hope you found it interesting. Now we move on to group theory in Rubik's Cube. At first we have to learn some definitions. If a non-empty set under a binary operation star satisfies the following properties, it will be considered a group. First property it has to satisfy is the closure property. A non-empty set G is said to satisfy the closure property under a binary operation star if A star B belongs to G for all A and B belonging to G. Second property it has to satisfy is the associativity property. If three elements A, B and C belong to G and A star B star C is equal to A star B star C, then the set G satisfies the associativity property. The third property it has to satisfy is the identity property. If there exists an element E belonging to G such that A star A equals E star A equals A for all A belonging to G, then the set G satisfies the identity property, and this element E is called the identity element of the set G under the operation star. Fourth property it has to satisfy is the inverse property. If for all elements A belonging to G there exists an element which is called the inverse element, I am denoting it with A prime. So A prime belongs to G such that A star A prime equals A prime star A equals C, which is the identity element, then the set G satisfies the inverse property, and such a non-empty set is called a group. There is also another property called the commutativity property, which states that if for all elements A and B belonging to G, A star B equals B star A, then the set G satisfies the commutativity property. And a commutative group is called an abelian group. But you have to note here that the Rubik's cube group does not satisfy the commutativity property, and hence it is not an abelian group. Now, before going into the details of the Rubik's cube group and proving it, we have to know certain things. At first comes the convention for an algorithm in Rubik's cube. Each letter here represents a clockwise term, counterclockwise if primed and twice if written 2 after it. When looking at that face directly, R denotes right face clockwise, L denotes left face clockwise, U denotes up face clockwise, D denotes down face clockwise, F denotes front face clockwise, and B denotes back face clockwise. R prime denotes right face counterclockwise, and the same convention is true for all other faces. Similarly, R2 denotes right face twice. Direction doesn't matter here because both will yield the same result. Now, when the moves are written in a sequence, they are called algorithms. For example, if we want to flip the orientation of an arrow on the centerpiece of any face on our supercube from parallel to anti-parallel and vice versa, or from 90 degrees clockwise to 90 degrees counterclockwise and vice versa, we apply the following algorithm. R, U prime, R prime, U prime applied 5 times in a row, which states that first the right face is turned once clockwise, then the up face once counterclockwise, then the right face once counterclockwise and the up face counterclockwise again, and it is repeated 5 times. And we have to note here that the sequence in an algorithm is very important, as the Rubik's cube group is not a commutative group. This algorithm, which is written here, this is shown in the next video. Please watch it carefully.
So the algorithm I am going to show you now is R Q prime, R prime Q prime 5 times in a row. So what does that mean? See, I turn the right face once clockwise, then the up face once counterclockwise, then the right face once counterclockwise, and again the up face once counterclockwise. Now, as I have to repeat it 5 times, so there are still 4 times left. So let's see what happens. Now this is the second time, third time, fourth time, fifth time. See, we get the exact same cube, exact same arrangement when we started in a normal Rubik's cube. Now let's see what happens in a super cube. Now we are going to apply the same algorithm, that is R Q prime, R prime Q prime 5 times in a super cube, and let's see what happens. R Q prime, R prime, Q prime. This is first time. The second time, third time, fourth time, and fifth time. Now you can clearly see that we have flipped from a parallel to an anti-parallel arrow. See, the arrow in the centerpiece is pointing in the opposite direction to the edge and the corner pieces. Now what will happen if I apply the algorithm another one time, like R U prime, R prime, U prime 5 times again. Let's see what happens. R prime, once, twice, thrice, fourth time, fifth time. See, we get back to the exact same arrangement of the centerpiece. Now we are going to discuss how a group is formed by a Rubik's cube.
I hope you understood the algorithms showed in the hands-on Rubik's cube video. Now we move on to the next part of our lecture. Now we consider the Rubik's cube group. G star, in which G is a set of all possible moves or a set of moves which are called algorithms, and the star denotes the binary operation of doing one move or set of moves one after another. For example, U star R prime denotes rotating the up phase once clockwise and the right phase once counterclockwise. And it can be easily proved that G satisfies all the four conditions required for it to be called a group under the operation star. First, since G is a set of all possible moves or set of moves, closure property is always satisfied for all elements in G. Secondly, associativity is also obeyed. For instance, U star D prime star R means first we turn the up phase clockwise, then a down phase clockwise, and then the right phase clockwise is again equal to U star D prime star R, and it is always satisfied for every possible set of moves. The third condition, which is the identity property. The identity element is when no move is performed, so identity property is also satisfied. There is also a case of a superflip. We are not going into that concept. A superflip is basically a set of moves. If we applied it once, then applied any arbitrary move after that, we get, say, a arrangement, and again we do that arbitrary move and then the superflip, we get the same arrangement. So that superflip acts as an identity element also, but it is a bit rigorous, so I'm not going into that. Fourth property is the inverse property. The inverse of any move or set of moves is basically the same move or set of moves done in reverse order. So inverse property is also satisfied here. Thus, our set G is a group. It is proved. So the set G accounts for all possible moves that can be performed and all possible arrangements that can appear in Rubik's cube and can be obtained through G under the operation star. I hope you liked this lecture on group theory and its application in Rubik's cube, which was presented to you by Juvenile Gurukul. Thanks for watching, and please consider subscribing to our channel for more quality content.